Let's see the design of crankshaft. Crankshaft is the main shaft of an engine which is converting the reciprocating motion into rotary motion. So crankshaft has different components: left hand wave, right hand wave. Here is crankpin, left hand journal, right hand journal. At crankpin, big end bearing of connecting rod is connected. So let's find out the dimensions of the crankshaft for the given data. BHP is 35 HP. Bore diameter is cylinder diameter as 100 millimeter. Stroke length 125 millimeter. Diameter of piston 99 millimeter. Engine speed 2200 rpm. Maximum gas pressure Pmax as 52.5 kg per centimeter square. Length of connecting rod 300 millimeter. Diameter of crankpin DC 65 millimeter. Length of crankpin LC 90 millimeter, and let the weight of flywheel as 50 kg. Crankshaft is considered as simply supported beam. We have to find out the different dimensions of crankshaft considering it is subjected to maximum bending moment. First consideration. Then second consideration is the crankshaft body is subjected to maximum twisting moment. So on the basis of these two considerations, the dimensions of crankshaft are to be find out. Then also the moments created by flywheel weight, belt tension, etc. are to be considered. Now let's have the first consideration, that crankshaft body is subjected to maximum bending moment. So here F is the maximum force acting on the crankpin. So it can be calculated as pi by 4 into d square into P max. D is diameter of the piston, it is 9.9 centimeter. P max is maximum gas pressure, it is 52 kg per centimeter square. Substituting the value, F its maximum force is calculated as 4041 kgf. So that is capital F, and small f in the figure is the distance between two journals. So small f equal to twice into A, that is 2A, that means A equal to small f by 2. So this F is calculated as 2 into cylinder diameter. So cylinder diameter is 100 millimeter, so it will be 2 into 10 centimeter, so it will be 20 centimeter, and small a is small f by 2, it is 10 centimeter. The reactions at two journals will be H1 and H2. So maximum F force, the maximum force F is balanced by the reactions H1 H2 in the opposite direction. However, magnitude of H1 and H2 will be same. That means H1 equal to H2, that is equal to capital F by 2. So it is capital F is 4041. So 4041 by 2, it is 20.5 kgf. Now let's find out the diameter of crankpin. The maximum force, due to this maximum force, crankpin is subjected to bending. So bending moment acting on the crankpin will be force, reaction force H1 into perpendicular distance. The perpendicular distance is F by 2, that means small a. So bending moment will be h1 into f by 2. Substituting values, it is 2020.5 is h1 into f by 2 means a, small a, it is 10 centimeter. So it is coming 20205 kg centimeter. Crank pin is considered as the solid section, solid rectangular section. So bending moment will be pi by 32 dc cube into fb. fb is allowable bending stress in the crank pin. It is 750 kg per centimeter square. Substituting the values of mb and fb, bending moment and allowable bending stress, diameter of crank pin is 6.49 centimeter, 65 millimeter, and length of crank pin is taken as the length of big end, and length of big end as per previous calculation is 90 millimeter. So the dimensions of crank pin as its diameter 65 millimeter and length 90 millimeter. Then the length of main bearing is calculated using empirical equation, that is 0.662 to 0.65 into cylinder bore is taken as 0.85 into 100, it's coming as 85 millimeter. So length of main bearing, so length will be same for both bearing, it is 85 millimeter. Now let's design the crank wave. Let's design the left hand crank wave. Here two crank waves are there, left hand and right hand. The dimensions of the crank wave are given by the empirical equation. Thickness is given by T equal to 0.65 into dc plus 6.35 is in millimeter. dc is diameter of crank pin. Substituting value of dc as 65 millimeter, T is 48.6 millimeter, is 50 millimeter. The width of crank wave is given by 9 by 8 into dc plus 12.7 millimeter. Substituting value of dc, width is 85.9 millimeter, 86 millimeter. So thickness and width of the left hand crank wave are 85 millimeter and 86 millimeter respectively. Left hand and the right hand crank waves are same, so dimensions of right hand crank wave will be same as the left hand crank wave. Now for finding the induced bending moment in the section of the crank wave, we have to find the modulus of section. The crank wave is in the rectangular section, so it is like this. This represents thickness T and this represents the width W. So here is T and this thing is W. So in the second figure T and W are shown. Now the section resisting the bending failure is the rectangular section. I mean, you can see at the top this thing is T is thickness and W is width. So this section is resisting the bending failure. If bending will take place, then how it will fail? It will fail like this. So here the failure will take place. So failure will be due to the reaction force H1 in the left hand crank wave, and failure will be due to reaction force H2 into right hand crank wave. It will be like this. Okay, so let's find out the modulus of section for calculating the induced bending stress. Modulus of section is given by the second moment of inertia, that is Iyy by y. Y is the distance of the neutral axis from extreme fiber. Here it is rectangular section, so Iyy will be Wt cube by 12 and y equal to t by 2. So Z will be Wt cube by 12 divided by t by 2, it will be Wt square by 6. Now let's find the value of bending moment acting on the left hand crank wave due to reaction force H1. So bending moment is the multiplication of force into distance. So force is H1, but how much is the distance? So distance is F by 2, means the total is A here, F by 2 A minus LC by 2. This thing is here with LC by 2 minus T by 2. So this is here T by 2. Distance will be F by 2 minus LC by 2 minus T by 2, and substituting the values, bending moment will be 6062 kg centimeter, and modulus of section, that is Wt square by 6, that is 8.6 into 5.2 square by 6. It is calculated as 35.8 centimeter cube, and this bending stress, induced bending stress, equal to mb by z, bending moment divided by modulus of section. So where from this came? We have the basic formula as bending stress by y. Y is the distance between the neutral axis and the outermost fiber is y. Is bending stress divided by y equal to bending moment divided by second moment of inertia, that is Fb by y equal to mb by I. So this Fb equal to mb by Iyy by y, and this Iyy by y means I by y is z, so it is mb by z. That means bending stress equal to mb by z. Substituting the values of mb and z, Fb will be 169.33 kg centimeter square. So this is bending stress, induced bending stress acting on the rectangular section of crank wave. Similarly, direct compressive stress is acting on the same rectangular section, and a force which is creating that compressive stress is H1. So direct compressive stress will be H1 divided by cross section. Resisting cross section is W into T. So the direct compressive stress will be 2020.5 divided by 8.6 into 5. it is calculated as 46.98. The total stress acting on a rectangular section of left hand crank wave will be 169.33 plus 46.98, it is 216.32 kg per centimeter square. And SAPE limit means allowable stress for carbon steel is 750 kg per centimeter square. So this induced value of stress in bending as well as compressive loading is quite less than the allowable value, so design is safe. Some values of allowable bending stress and allowable shear stress are given for different materials. So materials are shown here: carbon steel is alloy, cast iron is chrome nickel or some other alloys are given. So depending upon the material which we are using, we can find out how much is the allowable stress and how much is the induced stress. If induced stress is less than the allowable stress, we can conclude that our design is safe. So there will be no failure in bending and also in compressive loading. Then let's design the diameter of flywheel shaft. So flywheel is connected like this. Here is the location of flywheel. Let the weight of flywheel is W, it is 50 kg. Let the distance of a journal center, bearing center to the flywheel is G. So flywheel shaft is not supported. So bending moment acting on the shaft, flywheel shaft will be W by G. So it is 50. Let the distance G is 20.5 centimeter. So it is 1025 kg centimeter. This shaft is in circular cross section. So bending moment acting on the flywheel shaft will be pi by 32 d cube into FB. FB is allowable bending stress in the shaft material. Let it is alloy cast iron. So value is 450 kg per centimeter square. Substituting the values, the diameter of flywheel shaft is calculated as 2.918 centimeter. So let's have the diameter of flywheel shaft as 30 millimeter. The references for this presentation are given in this slide. So this is about the design of crankshaft when it is considered, means the shaft subjected to the maximum bending moment. Thank you.